Uh, Hi, everyone. My name is Pavan Nandakishore. I'm a data scientist at Coulibaly. I'm here with Ronay and Benedikt, who are both from NVIDIA. I'll sort of ask them to briefly introduce themselves. I'm also here with Joshua Hurst, who is from Zeller. So it's great to have everyone here. So today we're going to be talking about faster preprocessing and feature engineering for tabular data on the GPU. So both Ronay and Benedikt are going to tell us about how NVIDIA is doing faster preprocessing using GPUs in their sort of open source project called Merlin. So I'll let them sort of take it away, introduce themselves, and start their talk. So let me stop sharing my screen and you guys can share your presentation and just sort of, and then like Ronay, you can introduce yourself, Benedikt can introduce himself and then start.
Sure, Benedikt will start with this presentation, then I will show you a demo.
Yep.
Yeah.
So you can see this my screen?
Yep, I can see your screen.
Ronay, do you want to introduce yourself first, or do you want to introduce yourself afterwards?
I can introduce now. Hello, my name is Ronay. I'm a senior data scientist at NVIDIA. I am working at the recommender system team, working with Benedikt actually. So I've been working at NVIDIA since July 2018. I have a PhD in energy and power system engineering from Saint-Exupéry in France. And I was doing a postdoc before joining NVIDIA at NIST. That's it from my side.
Okay, thank you, Ronay. And yeah, I'm Benedikt. I'm working with Ronay in the team for recommender system at NVIDIA. I joined there a year ago around. Previously, I built recommender system at a German e-commerce, and I graduated from Columbia University in New York. And yeah, I will start with a presentation about a little bit the content about faster preprocessing and feature engineering for tabular data, and Ronay will show then a live demo and gives a little bit more details around it. Our library is mainly targeted through recommender systems, which often has a tabular data structure, but that doesn't limit it in any way that it's only used for recommender system. It's just like the use case we're building it for it, but you can apply the same techniques to any kind of tabular data set you have. So why recommender system? That's the perfect introduction why we work on this. It's like because it's like in the internet, like everywhere, like in digital content, in e-commerce, social media, and ads, and it's like really billions of users, meaning there's a lot of need to speed up these calculations and accelerate them, and that makes the user experience better and in general like lower latency. And it's like some studies say like 35% on Amazon is influenced by recommender system and 75% of what people watch on Netflix. So there's like a huge value of like using recommender system. And how the recommender system fits to tabular data. This is like an example on the left side. You can see directly, that's like an example in pandas output, how recommender system would look like. It's a table where you have like a user ID and then maybe some features like the age, then item ID, and then maybe some item features like price. And then you want to predict if someone clicks an item or buy an item, this example click. And this is our tabular data where click is our end target. And if you want to review a little bit, how would you build a deep learning model for it? Normally, how you apply tabular deep learning for tabular data sets is you use the categorical features and feed them through an embedding layer. The embedding layer just maps them to like a dense vector. And then you have your numeric features, which you may have to normalize first. Then you concatenate them together and then add some fully connected layer above of it. So it's a pretty standard neural network architecture, often used for tabular data. And often there's like the first challenge with this kind of architecture is the embedding tables. Like if you have really a large online platform with a lot of users and items, like 100 million of users, then you need to represent 100 million of users in these embedding tables. And these may not fit that easy on the GPU. And then we come like to the second part of why we need like customized software or special library for tabular dataset, is that the data structure and the models just look different. As I introduced in the previous slide already, if you look at computer vision, you have like a lot of convolutional neural net layers, like up to 100 or 1,000 layers deep. But in recommender system, you have often only a few feed-forward neural networks in the end, and then these embedding tables in the beginning. And these are like getting hard, and they can like exceed like GPU memory or even like CPU memory. And the second part is how the data structure look like. Often in computer vision, like ImageNet, a popular data set, they have like 1 million images, but tabular data sets, they have like 4 billion data points. Like it's like 4,000 times more data. And the data set size, like per data point, is like totally different as well. In computer vision, an image has like 100 kilobytes, but tabular data set, they have just a few numbers, which are like a few bytes. And this just has a totally different structure. And as this has a different structure, we can optimize our software to accelerate our network and training to leverage the structure and make it more efficient. And for the hardware, it's always interesting. It's getting like evolved over time. We like now at 80 gigabyte GPU memory. This is obviously increased a lot with like 1.8 terabyte bandwidth. And if this is not enough, we can pool them together. This is like NVIDIA solution, the DGX. We can pool 8 of them together. So you have 640 gigabyte of GPU memory. That should fit for most of the data sets, which you can load and do all the transformation. And if you feel like, oh, this is still not enough, you can pool these DGX together in something we call SuperPod. And then you scale them and have multiple nodes. And in each of them, they have like different kind of bottlenecks. Like if it's on a single GPU, it's everything one memory, easy. If you have multiple GPUs, you need to orchestrate like on which part is what is on which GPU. Then you have the bandwidth between the different GPUs. And if you have nodes, then the Ethernet connection is getting like the slowest part of it. And you want to optimize your software to have as less communication as possible, but you don't want to do this yourself. So our library helps to run this in the background in the best optimized way that it runs the fastest without configuring everything like on the lowest detail level. And for that, for recommender system, as I mentioned, you can use it for any tabular data set. We see like different stages and with different problems. So we have ETL, which often needs to pre-process and feature engineer, which can have a complex structure. And if you run it on the CPU, it can be slow. But as it has on a GPU, a lot of small cores and this super fast GPU memory, we can accelerate it. And Ronay will show like a demo for Mb Tubular, how to accelerate these ETL part. And this is like the main topic of the talk. Just to give a total overview, after you do like the ETL, the pre-processing feature engineering, you want to train your neural network. We provide there like a custom plugin for TensorFlow and PyTorch to accelerate data pipelines, as often like the data loader are more written for computer vision or NLP. We wrote optimized data loader, which loads the data into the GPU and shuffles there and do all the operation with speedups. If you need to scale these embedding tables to like large models, we have like huge CTR, and they distribute the embedding tables over multiple GPUs or multiple nodes. And finally, after we train all this, it has to be deployed. And there we have like a solution just called Triton, which is an inference server and deploys deep learning model in production, all with a few lines of code.
So I'm just going to ask a question there, if you don't mind, Benedikt. And for everyone, like, feel free to put out questions so that we can ask them as we go along if there's anything specific. So when you talk about these embedding tables, right, how sparse are they? Because if you have sparse tables, wouldn't the architecture have to be a little more different?
So the embedding tables are often, like, as you say correctly, for sparse features, like for example, user ID, but okay. So it maps user ID 0 to like a vector of 64 elements, and these then are dense. But then you have maybe, if you're like a large online platform, you have like 100 million users, So you have a table 100 million users times 64, and these are can be really large. And we saw like examples going up to 500 gigabyte or terabyte. And then you want to optimize in terms of how do you train your model, either like over multiple GPUs, or we have something which is called model oversubscription. As you said, it's sparse. You do not need all embedding vectors for all users into GPU memory. So if you train on a single node or single GPU, you load a fraction of the data into your GPU, or you load a fraction of the data in your GPU, then you load only the embeddings you need for this fraction, you do multiple batch updates, and then you sync it back to a parameter server. And the reason that this is efficient is like moving a big chunk of data once is efficient, then you do all the updates, and then you move it back.
I see. That makes sense. Awesome. Thanks.
Yeah, we will unfortunately we have this like up to 4 to 6 hours of the talk. We focus on the first part, but yeah, if there's interesting like this, if you look for HugeCTR GitHub, there's like a lot of examples and explains in a lot of details how to apply these. Then a little bit why focus on the ETL part. The experimentation pipeline often for tabular data sets looks like we have our input data, then we do some pre-processing and feature engineering, then we train our model, and then we move back. And we saw that often the pre-processing feature engineering is a really important part, and most tabular data science competition are won in that area as engineering the feature, like providing information, a better structure to the model, improve the learning. And we look at the history of the Rexus challenges, which is like one, it's from the Rexus conference, which has like a continuous every year competition with it. We can see that often the winning solution engineered a lot of features. Like we participated last year and won the first place, and we built 150 additional features to the raw data. The year before, they built like 250 features. Before that, they did a mix between CNN and XGBoost, and it just said they did like extensive feature engineering. So it was always important to do feature engineering. So we need to work on the stages. And as we competed last year and actually the year before, like last year, we built a pipeline which took like original 2 days. If we optimize it on CPUs, also on CPUs, if we optimize it on CPUs, it still took like over an hour, but we can crush it down in something like to 20 minutes or even like to 2 minutes by using 4 GPUs. It's not like we need a huge cluster. It's just like using the right tools and optimizing the framework helps to speed up. And as we then be like 20 to like, I don't know, 100x faster, we can do so many more iterations, so many more experiments, doing more feature engineering, and that helps. And that should illustrate a little bit the right side. If you do it on a CPU workload, you starting your ETL, this takes some hours, that you take your coffee, you get your next coffee, then you realize, oh, you forgot to add the feature, you have to restart the full pipeline, then you realize that you have maybe a bug or you forgot to impute null values and you have to restart again, and you're always debugging. And if it takes long, it will never end. And in comparison with the GPU, and that's what we experienced really last year, you can just do 10 experiments a day, and then it's getting all faster.
So just clarity on the last slide, right? In the Rexus Challenge 2020, the Intel Xenon, that's a CPU. So how long did that take? That's in seconds.
Like in seconds, it's like almost an hour.
Almost an hour.
Yeah.
Yeah. Oh, that's 3670. And then you're saying that, yeah.
But this was already optimized. Like it's not like we could prototype this kind of code. It was really then okay. To have a fair comparison, we said like, oh, let's sit down and really try to optimize it.
Yeah.
The course. But during like, if you really prototype and experiment and feature engineering is not like the, let's say, best optimized code, we see like bigger, let's say, speed up in comparison, because then you not have the most efficient pipeline organizing all features in the best way. And then we see like, oh yeah, maybe then we're not getting to the 2 minutes down as well for GPUs, but it makes a difference there.
Yeah.
So why do we need feature extraction just to relate it to computer vision? Like we heard a lot about deep learning is automatic feature extraction, and we just give the raw data. But for tabular data, it doesn't really work. And that's because of the structure. It cannot relate to previous rows. Like it can only look at the current data example. And there are some attempts to build architecture for tabular data, but often it's like some fully connected layers, and you have to do the feature engineering manually. And that's the reason it's important that we can speed up these paths. Some types of feature engineering have like categorical ones, which we can do like something like target encoding, count encoding, categorifying, unstructured lists, where we can do the same. Numeric ones like price, delivery time, where we can do binning, normalization. Then we have time stamps, where we can extract like month, weekday, weekend, time series, where we can count how many events do we had the last hour, the last day, and so on. And then image text, where we can use like some other deep learning architectures to extract the latent representation, and then social graph and geolocation.
So let me sort of, sorry, interrupt again. So one of the points here, I think that's important to highlight is the fact that what you're doing is because typically in in deep learning, you don't have to do any feature engineering, yes, right? So it automatically, like, that's the whole idea of it being a feature extractor.
It's often for like computer vision and NLP. For tabular data, it's often better to do feature engineering, okay, as it will help the model to learn faster and extract patterns.
I see.
At least for experience. And we did it like in different competition, and feature engineering was always a key.
Okay, so I think that's an important point to highlight, because I don't think that, like, because a lot of people would have seen a lot of computer vision and NLP applications, but they wouldn't have seen this. So this is really interesting that, okay, when it comes to tabular data, you have to do feature engineering before you even feed it to a neural network. So that's, I just wanted to highlight that point for
and just to give you what's like, you can use like tree-based models and deep learning. You could use it with both. Then you have like types like CatBoost, XGBoost, Light GBM, and they split it by information gain. The difference is tree-based often doesn't need normalization of the numeric features, and deep learning models, they need it. Otherwise, you have exploding gradients and it will learn really slow. And there's like the same architecture we had like in the beginning of the presentation. There's like subtypes like wide and deep, DeepFM, DLRM, which often just is a different combination of categorical and numerical features. Focusing on Mb Tubular, which will Ronay present soon. From that point, there was the idea that we said like, oh, we want to speed up the first part, which is the ETL, the feature engineering and pre-processing. And we wanted to design a library to quickly and easily manipulate terabyte scale data. And the first part is of obviously the speed. So we achieved like 10 times speed of comparison to CPU. But then often the first question would be, yeah, but GPU memory is only like 32 or 80 gigabyte. That doesn't fit the data set. So we built a library which scales to unlimited, or like no limit on a data set. It will load the chunk of the data set into GPU memory, apply the transformation there, and store to disk, and will automatically partition it in the right way without any need from the user. And we have the usability. It should be easy to use, a high-level abstraction, and just a few lines of code, with often all these feature engineering techniques already implemented, where we can just chain them with not knowing like to re-implement always the best practices. Here's like an example workflow with like 10 or 20 lines of code. Ronay will show them soon. And you see in the first bullet, or the first line, is like how you chain them. So you say like, oh, this is the column names. And then you say like, oh, please categorify them. And this will automatically make continuous integer out of them, maybe frequency threshold. Or the second one is continuous columns, fill in missing values with zeros, clip them, apply log operation, normalize, but you don't have to write, oh, let's collect the mean and then the standard deviation and then subtract them and divide by it. It will do that automatically. And there's like more complicated ops behind it. And afterwards, you just define like data set and then say like, please fit and train and then transform it to it. that's all the operations available. I will not go through it. It's just like an overview that we implement them continuously. And if you are interested in the library, check out our GitHub repository. And if you have an operation which we don't support yet, feel free to write a feature request. We are always happy to get feedback. And if there's a use case, we are happy to help to implement them. A short background is under the hood, it uses QDF. QDF is a kind of data frame library for GPUs with a pandas-like API. It's really almost like you can import QDF as PD and will run the same code you use for pandas, but on the GPU with speed up times 10 to 50x what I saw so far. And if you really need to scale it, there's something called Dask, which is like just a library to parallelize and scale Python code. And what it does, it splits your data set into multiple partitions. And this partition could be a pandas data frame or a QDF data frame. So we have like Dask QDF splitting your data set over multiple GPUs in partition and apply all these operations. The last point, to show how fast it is, Criteo-Ed is like the largest available recommendation data set with 1.3 terabytes of uncompressed click logs. That's 4 billion data points. And the official NumPy ETL script took like 5 days. It's like 7,200 minutes. And then for the same reason, we want to have a fair comparison. So we spent time to really wrote an optimized Spark solution for it on CPU, which took still 3 hours. If you use a single GPU, we need only 30 minutes for the same ETL. And if you use 8 GPUs, we get it down to 2 minutes. So we get like 100 times to 3000x speedups. And that's, yeah, you can run more often your ETL scripts, you can train more often, and that's, you get a lot out of it. I think that's the end of the presentation, and Ronay will walk you through an example in a live demo.
So one of the questions that came up was, do you mind sharing some of these slides, Benedikt? Because I'll just send them to me. I will share it with people because there's a lot of material and a lot of interesting things, and people would love to sort of explore more with it. But yeah, that's super interesting. So Ronay, you can go ahead.
Yeah.
Can you hear me? Okay, I'm going to share my screen. Okay, should be that one. Can you all see my Jupyter notebook?
Yep.
Okay, awesome. So thanks, Benedikt, for this nice presentation. One of the questions was actually, Benedikt, I answered. It was about, is feature engineering really making a big difference, and can you tell what is it with and without? Actually, yes, for the tabular data, it is really making a big difference. As Benedikt mentioned, that it is really helping us to, helping the model to learn some information. It's different than this CNN models or NLP techniques. So I will show you, I will walk you through a feature engineering and pre-processing example using NVTabular library. So NVTabular library is the ETL part and the data loader part of Merlin framework. Merlin is an end-to-end framework for accelerated data loading, data preprocessing, training, and inference. So it's an end-to-end framework. But here, in the interest of time, I'm going to only show you an example how you can do feature engineering with NVTabular. So two things actually important. Feature engineering is required. How much feature engineering you will do, that depends on you, for sure. Second thing, how fast you can do this. So Benedikt mentioned that, so if you spend like hours and hours to do feature engineering instead of spending minutes, what is your advantage there? You can actually explore more features, right? That's the idea. So when you can, if you can explore more features, you can try if a feature that you created is going to boost the performance of the model or not. So you will have some time actually to explore more, to create more features. If things takes like hours and even like maybe a day, that will be a little bit like, I would say, frustrating. So you might say, okay, I'm done with a couple of features, that's enough because it takes too long. Okay, so let's get started. First, in this demo, we are going to use a data set It's an Amazon review data set, but doesn't matter what data set we are using here. So we start by reading the data in, okay? And we are using QDF, which is QDF is a GPU data frame. Benedikt already told you. So what we have in here, actually I already ran my cells. We don't have to run everything, but I will do live demo. So you can see that we have a string entries, user ID, product ID, right? They are string entries or brand, and cat0, cat1, cat2, cat3 columns. We also have numerical entry, price, and label column. Actually, label column, it looks like a float, but we can convert it to binary later. So this is our data set. We have some columns, some of them are categorical, some of them are numerical, okay? We check if
Ronay, just a sec. In the data set, what are you trying to predict? Like, what is your target?
So in this example, because of the time constraint, unfortunately, we are not going to show you a neural network example. We will only show you how we can pre-process and create some feature around this data.
Okay. So this is the feature set, essentially.
Yes, exactly. Actually, we could have just created easily created, for example, TensorFlow model and MLP, multi-layer perceptron with TensorFlow, by just like using the label column, which is our target, right? Imagine the label column is a review or rate by the user, a rate given to this product by this user. So think it in such a way.
Okay. So yeah, just for clarity, each row essentially here represents a product, and you have a user ID which describes a user, and then you have various features for that specific product. And
exactly.
Awesome.
Thank you. Exactly. So we have like features about the price of this product, the brand, some categorical information about this, and the timestamp. So we will convert this timestamp to datetime object now. I will show you. So we are first checking if we have any nulls in this data set. We do. Brand and price columns, they have some nulls. We will deal with that. So we know that, for example, if you feed a data frame with nulls to certain models, certain frameworks, they wouldn't like it. So you might want to treat them right in advance. So let me take this here. Let's talk about NVTabular a little bit. So how NVTabular is working. I mean, we can start by reading data and just define the paths of the data. Our data is in Parquet format. It could be in CSV format or Avro different. So we can actually play with different data formats. That's fine. But we have Parquet format. It's a compressed data format. It has advantages. So first of all, when you start with NVTabular, you want to create data set objects. So the goal is this data set object actually, first of all, you can create a data set object from different data formats. Here we use Parquet. That's why we set the engine as Parquet. But this data set object actually, the purpose of this, it's a wrapper class to provide the internals of NVTabular with a reliable mechanism to translate raw data into a Dask collection with appropriately sized partitions. So under the hood, we are using QDF, and also we are using Dask QDF. So this is important. We need to create dataset objects. That's an important wrapper. Then later, let's start with defining our operators. What techniques we would like to apply to this dataset to convert the dataset or to create new features. Remember, we said that price has some missing values. It's a numerical columns. One technique we can do, we can calculate the median of this column and fill the missing values with a median value. How we do this with NVTabular, basically, we have an operand. You can see this right shift operand. And this right shift operand, it was actually creating a chain reaction here, because we take the column, we define our column group that we want to apply a certain operator. We define our column group, and which is price. We say that, okay, we would like to apply this operator, fill median, and we also want to apply another operator on top of it. meaning normalize. Here, normalization is going to do standard scaling. So basically, we will do both. Sorry, we will do two operators, pre-processing technique here in one line. Okay, that's it. If you do that, we will apply this to price, and we can, of course, check the, because this is a graphical representation, and we can check our graph, visualize our graph, and you can see that input column and the output column. So output column name didn't change, just the output column was, input column was transformed, right? It started as price, it ended up price, but it was transformed. So it was not transformed yet, it will be, because we didn't start the workflow pipeline. We need to start a workflow pipeline, which is with NVTabular. Workflow is orchestrating everything. Then, as you do with the scikit-learn, right, you do fit and transform. We are applying the same thing here. By doing a fit method, basically we are collecting statistics, global statistics from the train set. And by doing transform, we are applying this global statistics both to train set and also validation set. So we could just have a validation column here too. Like the same thing, instead of train data set, we could call it a validation data set, that's all. And this will actually generate us our output column. Price is actually, look at the price. It has negatives because it was normalized, right? It's normalized in a way that it's now it is mean is almost 0 and the standard deviation is 1, right? That's it. Yep. Another technique we use often, logop, which is taking the logarithm of a column. If the column has a very skewed, right, very skewed distribution, that's another technique actually we do. So here you can see we are just showing you two plots of the product ID column, right? And we are showing you actually the counts of this product ID. It's pretty skewed. You can see that, right? And so what does that mean? So some like products only showed up once, for example, or very few times, but the frequency of those showed up few times is quite a lot, right? So we call it like a power law distribution here, very skewed. And if you want to apply a logop, maybe you will get more like normal distribution type or type. So it might help for the learning. So how we can do this, how we can apply the logop? First of all, let's say which column we would like to do this. Well, we will see it here. First of all, do you remember I said that brand column has also missing values? Maybe we can fill the brand column missing values with by using fill missing operator. This time it's not fill median because brand column was not a numerical column. So we can just replace the, as far as I remember, brand was a string column, right? We can replace this null values with 0, which is fine for this example because then what are we going to do? We are going to create the counts for every column. Basically, we will calculate the frequencies. Why this is important? For example, here we are creating an extra feature. Why this is important? Because in recommender systems, popularity is an important feature. We would like to know how much, or interactions, right? How much interaction a user is performing, how much a product is interacted by users. That's also important feature. That's why we are doing a count encoding here. Basically, this is like group by count. Okay, that's what we are doing here.
So just a question, when you're filling the missing value for brand, right? Are you also then categorically encoding it?
Not yet. That's a great question. We did not use categorify up. We also have a categorify up. That's a perfect question. No, it's just going to, it's not going to encode it yet unless you call the categorify up. Yeah, we also have an up called categorify. I don't think we have it in this example, but that's a good point. We do have it. And in the categorify up, actually, we have a lot of functionalities. You can directly encode all the categorical features. You can do hash encoding with the categorify. You can do frequency hashing, meaning that you don't hash everything, you hash some certain features with less than a certain frequency, etc. So yeah, we have this up to. Okay, what we did here, I will show you. We are creating extra features, frequency features here, and here we are basically, we calculated the counts. Now we will apply the logarithmic operation on top of the counts. Basically what we are doing is exactly what's happening in this plot. We are calculating the counts, which is a histogram, think about that, and then we are applying a log operator on top of this histogram. That's what's happening here. So basically just we can do this. Actually this is just a one-liner code. You just define your column groups, which columns you want to apply an operator. This is a column group coming from previous operation. So see that chaining reaction. So you create features, you take these features, apply on top of these features another operator, meaning there is a good chaining here. Okay, then again we can visualize our graph. We can see easily what is happening here under the hood, which columns are taken as inputs. From here, it is ran from here, the other columns, and then we apply a join group by. Basically, with the group by operator, we are calculating the counts, and then on top of it, we are applying log-up, and then we just rename the new columns, and voila, that's it. So we will do the same thing here. We will create our workflow first, and then we will do fit and transform. That's it. And what is happening here, if you notice, there's a two-parquet method here, meaning that I can write back my process data into disk as a Parquet data frame. As a Parquet data frame, basically in Parquet format. So I read from disk, I write back to disk, and so this can in this method I can even say that how many Parquet files I would like to partition my entire output data set. If I want to write it as an output files, 10 output files, I can do that. And that we have this such parameters you can use in here. So this is going to give you, actually I would like to run this too. So what is happening here? Look at the big one here. See this all extra columns we just created, product count, user count, product count again. So we created all these count features. And we also take the logarithm of these count features and we keep all the columns together here. Just for the demonstration purpose, you don't have to keep everything. I mean, if you want to remove count columns, then only keep the count log columns. Of course, we can do that. Hope that makes sense. Just to show you that you can basically create new features, and all these new feature columns will be added to original data frame if you want to. That's it. So you see, we have a bunch of new features here. Okay, so we talk about logups. Now we are going to talk about another very important method, the technique that we use a lot, right? We use lambda. You know, you are familiar with the pandas, and I'm sure many of you are already using lambda up. So now with the lambda up, we can actually apply user-defined functions. So here with the lambda up, what are we going to do? You remember we had a column. It was review time, Unix review time. If you remember, it was a timestamp column, but it was not in the right format. It was not in the date time format. First, with the lambda up, we can easily convert this to date time object, which is this line. Then I'm going to rename it. The reason I'm renaming it, because I would like to keep the original column too. So if I don't rename it, it will replace the original column. But if I want to keep both, I just want to rename my new column, okay, just to avoid confusion. So this is it, just like with one-liner, as in pandas, you do pandas to date time, right? With lambda, you can do it. But the idea here, you do here with the accelerated library. So this, what is this? This is converting you remember the label column? It was the rating from the user if imagine that I would like to create a binary classification model, where if I say, okay, if the rating is bigger than 3, let's assign the value as 1. If the smaller than 3, let's make this rating 0. So it will be basically a 0, 1 column binary, right? That's what is going to happen here. It's again by using just lambda function. So you just call the lambda up and create your user-defined lambda function. Here also you can change the type of this column. Basically, that's it. And then this is an important part. Actually, I am sure most of us doing this. When we get a timestamp column, most of us are trying to create some temporal features, right? Can we extract a day? Can we extract a day of week? Can we extract the hour? Is it a month or season? You see what I mean? Year. We just create these extra features, right? All of them are temporal features. And then we can do this easily with just lambda up. And you can see with the column group, I just defined my column group. And this column group, if you notice, it's coming from here. It's the result of this, because I have a datetime column now, and I'm applying a dt.day. I'm extracting the day by just doing this call.dt.day, right, as in pandas, right? That's it. And same for the month, same for the year. And I will have 3 extra features. I will have day column, month column, and year column. And okay, so here, again, I can actually just sum all my new feature columns and name them as the time features, and just create my graph. Voila, you can see. So we will again do the same. We will create the workflow. In the workflow, we will just feed inside our all features that we want workflow to apply these operators. And then we will just use the fit and transform. And to Parquet, we will just write process data back to disk. And then, okay, let's see all the columns that we just created. Actually, we have more than this. Here, there's the filtering, so I can show you all columns we just created. Okay, so check this. We have a new column, date time. We have a day column. We have a month column, year column, right? And check this. Remember, the original label is like that, but we created a binary label. At the end, when you create your model, of course, you can drop all the columns that you don't need. That's it, right?
Yeah, you can drop the original columns and you can use the new features.
Exactly, new or transform. So another operator is join external. Join external is basically the merge. And merge, actually, it's an important technique that we do a lot, right? To see that we are dealing with multiple data frames, and we create something on the one data frame, and then we do something another, and we would like to just merge them. That's an important, operator we need actually in our day-to-day data science activities. So for that, we use join external, and we can support left and inner joins with the join external. If you notice that I just read a new data frame here, other than my original data frame. This is a new one. And what is happening? There's a product ID column here and some sales information, okay, about this product. So what is common with the original data frame and this one? It's the product ID column, right? Both have this product ID column. That means I can merge them.
Yep. So it's like having like new data that you may have collected about same set of products, some other information that you're pulling in. Right?
Exactly.
So this part is essentially like what you would do in SQL, where you're just doing like inner join, outer joins, essentially just joining data.
Yeah,
right?
Exactly. Essential joining, as in SQL, as in pandas, essentially merging the tables, right? Based on a given key, there's a unique key or say secondary key, whatever key you want to use, right? Okay, so that's it. So you can just do this, apply the same, oops, sorry. So you might say that, oh, each time do we need to do this work, fit, transform? No, you can do it only once, since we just break this down to, separate sort of like demonstration for this demonstration purpose. We just break it down to different operators. That's why each time we are applying this. But in your pipeline, you can create the pipeline and you can just do the fit and transform only once, or as many times as you need. That depends on you. So what you see, if you notice here, we actually with the join external, look at here, we had the external data frame, and basically we'd say that by using the product ID column, join my original data frame with the external data frame I just have on this column. How? Just like with the left join. It's very similar to pandas, right? On and how you see. Okay, so I think I ran this. If I did, I don't know if I... Okay, so that's it. We just joined them. You can, again, this is filtered. We can maybe see that you can see here, actually we just joined with the original. So you can say that how they were joined with the original. So you only see the product ID, you are not seeing different other columns from the original data frame because we didn't choose them. If you notice here, we only choose the product ID. If I choose multiple columns, I would have all of them. So one last technique I would like to talk about is the target encoding. It's a very useful technique, to be honest. And this was like a technique that helped the team, NVIDIA team, to win the Rexus challenge last year. The Rexus challenge with the Twitter data. And target encoding was actually like a magical feature engineering technique. So target encoding, basically, it calculates the statistics of a target column given one or more categorical features. So we apply the target encoding to categorical features, and we actually, it is basically calculating the conditional probability given a target. Given a categorical feature. So if you look at here, you can see it's very simple. So you have a given category and you are calculating the probability that this target will be 1. Basically, you are taking the mean of all the target values given a category. So what is happening here? You have all these categorical features, right? If you remember, Benedikt mentioned about this embedding tables, how sparse they can be, how compute extensive they can be. Imagine that you are just replacing all of your categorical features with numerical features by using target encoding. And target encoding actually really revealing information about this category, it is, as I said, estimated probability where the target could be 1. Okay. So for example, the probability that a product will be, probability that a product was clicked. So you can actually calculate such probability, okay, by using target encoding. As I said, it's a very useful feature. And we have this operator. So if with one line of code, you can just apply this target encoding to the categorical columns that you choose. You don't have to apply it only one column. You can even apply it to the join columns. Okay, so like categorical 1 column, 2 column together. You think this as a cross feature or feature crossing. So
just a question, Ronay, sorry.
Sure.
So what happens if your test data does not contain some of the targets that you might see in the wild? Like,
yeah, that's a good question. So in that case, I think you can assign the global mean directly from the train set. You calculate the global mean and you can assign the global mean.
That makes sense. Yeah. Go on ahead. Sorry. Yeah.
Yep, sure. That was actually a very, very good question, to be honest. Very good question. So you don't have to do target encoding only like in the classical way, like you have a train set, you calculate all the target encoding based on train set and apply it on the test set. You can also do like k-fold target encoding, let's say, or it is very similar to cross validation, right? So you can divide your train set to folds and then apply the target encoding to the fold that you to the fold that you are holding out, right? By using the other fold. So you can also do that. There's also another parameter called smoothing parameter, because why we have smoothing parameter? The thing is that target encoding can be prone to overfitting, and smoothing helps because imagine that if certain observations are very low, like their frequency is very low, so at that point smoothing can help. So if the number of observation is low, we might want to use global mean. If the number of observation is high, we might want to use the mean of this category value. So its own mean, right? But if we have low, as I said, it might create some issues, and that's why we would like to have a smoothing parameter. Do we have the function here? Yeah, look at here, smoothing parameter. So it's basically if you give a very big value for the smoothing parameter, it will relate to that target encoding will be closer to the global mean. If you give it smaller, it will be closer to the mean of this category value. So it's somehow like finding a trade-off, and you can just adjust it. Okay, let me show you how it works. So which columns we would like to do target encoding here? Okay, apparently we are applying some operations here. Again, let's do this. Okay, so which columns are we going to? This is just a lambda up. We just did just to show you again the same operations we just did. And this is what's going to happen here. I'm defining my categorical columns that I would like to apply target encoding on top of it. Okay, so I have categorical columns, these columns. I have time features, these time features, and then I have combined categorical columns, meaning that joined. As I said, think this as the feature crossing. These two are combined together. So conditional probability, but when these two given together, okay? And then I'm going to apply the target encodings on top of these three feature columns. Okay, the reason we just created this, just to show you again the time features, and then with just one liner, if you look at here, actually there's a big algorithm behind, right? But it's just one liner. If you just write this code by yourself, it will be half pages. But with NVTabular, you just apply this. You just call it target encoding. And then what you do, label to binary. And then, so why this label to binary? It is our target column. Remember, we converted the target column to binary column. And then k-fold, we don't do multi-folds here, just for the demonstration only one, and the smoothing parameter is 20. And that's it. Okay, so if sorry, go ahead. Sorry.
No, cool. I mean, this is nice. You can define this graph and you can actually see. I really like this part. It really helps visualize what's going on.
Definitely, yeah, I agree. Actually, it's also great for debugging purpose.
Yeah.
And then you can see all these new columns, features that we created. These are new features we just created. And let me do this, and I will just stop here, just take the questions. And the final workflow, you can just put all of them together. We don't have to do that. So I guess you got the flavor. Look at here, all our newly created target encoding columns. Did you notice something that this is, did I apply something? This is like, basically it should be, target encoding column should be between 0 and 1, okay, because it's a probability. So let me show you the original again. Oops, yeah, so what we see, we can see that everything is here, new feature columns, okay, and then originals should be here, user ID, product ID, brand. As I said, when you just feed this data frame to, let's say, like a TensorFlow or PyTorch model, you are not going to use product ID as a string anymore, or user ID or brand. Instead, you will use either their encoded version or the new target features that target encoded features that you created. Well, that's it. That's it from my side, and I'm happy to take the questions.
Yep. So I think one of the questions that came up was, so Brian is saying that I love seeing all the clever techniques you've used. I would still love to know how much model improvement was gained in prediction success by detailed feature engineering.
Okay, sure. Yeah. Okay, Benedikt, do you have the slides again? Can you mention like your recommender system journey, like with and without target encoding? Have you won the challenge with the KGMon team, you guys?
So, I think to answer it's highly depends on your data set now, on your data set and about the task you try to predict, how big your data set is. I guess it's really small. It's difficult. For one data set, which is a public data set for e-commerce, we saw like between 6 and 12% improvement.
Okay.
I'm thinking about, we worked in January on the VSDM booking.com challenge, but I think it was like around 10 to maybe 15% there as well.
I see.
That's the kind of uplift, like from the model you have, and really like the model, and just by adding new features or more features, doing the feature engineering to improve. Of course, if you have like a data structure, which is like, I don't know, you have string as categorical ones, you cannot feed them into embedding layers, your accuracy will be 0. Like there's like a way you can train a model with like categories as strings. Like there's like a minimum of feature engineering which should allow you, and by just then adding more features and better features, I would say like 10 to 15%.
I see.
But it really depends on your data sets.
Yeah, I think that makes sense, right? Because in many ways, like you don't know what kind of patterns are there in your data, and what kind of features you need in order to actually train it effectively. So you have to basically play around, and that's why forget training the model. It really becomes important to like explore your data really well, right? And I completely get that. Like it's not always clear what sort of, what is the best accuracy that you'll get out of this. So I do have a couple of questions. I know we're kind of we're just like short of time. So what do you guys envision this to, like, so this you've built for recommender systems, but I can see the applicability being there for other tabular data sets, right? So are you guys looking at different types of tabular data sets and different types of applications beyond recommender systems?
Currently, we particularly focusing on recommender system type of data set. We have an example for other data set, but the applicability, as I said, it has broad applicability, and I mean, why not like exactly also market it to be used in healthcare, or to be used in I don't know, in even in maybe supply chain or some other domains, or manufacturing domain. Like in healthcare, it can be used for the medicine recommendation, right? So it doesn't have to be always in e-commerce, definitely. So I mean, we have also Kaggle examples that we put to Kaggle for the Kagglers. They can take and use it for their own tabular data. But like internally, our focus basically on recommender systems. But it can be, as I said, it can be used for, it doesn't have to be a recommendation system. It can be any tabular data, right? If I have a tabular data of, for example, for the wind prediction, and I'm collecting all the like the wind data, or the air or environmental variables, etc., humidity, temperature, etc. I can still, because it's a tabular format, I can still use NVTabular, right? Easily to create features and to process my features. So why not? Exactly.
Yeah, fair enough. Awesome. So
Benedikt might have extra some.
Benedikt, your thoughts?
My thoughts? I agree. Like, I think in general, it can be used for any kind of tabular data. We are focusing right now on recommender system because like you collect so many click logs in that domain, where you get to these like data sets which are like terabyte sizes, where we need these kind of solutions. Like, if you can solve these ones, you can solve the smaller ones problems as well. And there you have these like huge data sets, and they're like in a lot of companies a problem, and that's what we want to solve right now. And of course, and I think if your data set is maybe too small, like let's say like only 100,000 lines or like rows, you can still use it, but you may not get the speedups out of it, because like you need a certain data set size that you like if it's instead of 10 minutes 1 minute, I think the 9 minutes I would get the coffee in the time.
Yeah. I think a good plot would be to actually like do exactly what you're saying. Really have basically a plot that tells you, like, if you have, you know, small data set, medium data set, large data set, what is the kind of speed up time if you get if you use these sorts of techniques, right? That would be something that would highlight exactly like what kind of speed up you're getting out of this. So with this, I will have to close because we're kind of out of time. So I thank Ronay and Benedikt for this really great talk. We got to learn about how to do feature engineering with tabular data with NVTabular, and thank you so much for being here. So you guys can give us the GitHub link, right? I can post it on our meetup group so that people have access to that, and also the slides. But yeah, this has been a great learning experience. So thank you so much for coming, and everyone have a good day.
Thank you everyone. Thank you, Puan.
Yep, thanks.
Thank you so much.
Thank you, Brian. You're welcome. Bye.
Yep.
Bye.